Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back to discuss the solutions for homework number 5. This is going to be a discussion involving problem number 1. Each of the homework sets in the 5th week involve the use of VEDA simulations, and by now we're assuming that you'll be able to go in and execute a successful VEDA simulation, provided we give you input parameters. So most of these problems I try to set up some plausible AFM question. I provide the necessary parameters that are required for you to actually run the VEDA simulation. Once the VEDA simulation is run, then I just ask simple questions about the results of the VEDA simulation. And if you've executed that whole process successfully, it should be a simple matter to go in and in most cases just read the answers right off the VEDA graphs. To aid in this process, at the end of the homework set, I've attached some worksheets. These are sheets that I've made up for my own use. They kind of help me remind me of what parameters I entered in and what day and what problem I'm working on. So if you find these blank worksheets useful, great. If not, that's fine too. So let's get to the first problem. The first problem is to answer the question, are there some simple measurements we can do during an AFM experiment that might tell us whether the tip radius is changing as we work our way through an experiment. And so we're going to run a VEDA simulation to investigate whether we can read off some simple measurement and monitor that during the course of an experiment to ensure that our tip radius is reasonably fixed. So the way this problem is set up is we've got a cantilever. The spring constant of the cantilever is 1/10 of a Newton per meter. This cantilever interacts with, or the tip on this cantilever interacts with a flat substrate. The modulus of elasticity of the substrate is chosen to be 100 gigapascals. We're going to let the tip interact with the substrate by way of the DMT contact model. And the strength of the long-range van der Waals interactions is going to be specified by the Hammacher constant, which in this problem is 3.4 times 10 to the minus 20 joules. So the whole issue revolves around a magnified view of the tip. Of course, you can't see that during an AFM experiment. That's one of the difficulties with AFM. You never really know what's going on at a microscale or at a nanoscale between the tip and the substrate. All you can do is make inferences based on measurements. But we pretend that the tip is essentially a sphere, radius arc of tip. And we're going to do simulations using VEDA in which we vary our tip and then see how, let's say, the force distance curves change as the tip radius is varied. So to execute this simulation, you have to go to VEDA and you have to select the force distance curves application. When you select that application, then you'll be able to enter in these various parameters that are relevant. And what you're basically doing is you're generating force distance curves. The range of the force distance curves is about 0 to 3 nanometers. So somewhere out here is about 3 nanometers. Right? This is 0. So this is the range, the relevant range of Z that we're investigating here. And what we're going to do is we're going to run a sequence of force distance curves where we systematically vary the tip radius. The minimum tip radius is specified in the problem as 5 nanometers. The maximum tip radius is specified in the problem as 15 nanometers. Now, if you've executed this program correctly and you select plot all in VEDA, you should see a sequence of curves that roughly resembles this. Each curve is offset from the other because there are different tip radii involved. So this result immediately suggests a way that you can measure the tip radius, right? You can possibly monitor the tip radius by measuring the jump to contact point, for different force versus distance curves. So, for instance, if you did a force versus distance curve at the beginning of a day's worth of experiments, and you got a curve that resembles this first red curve, this jump to contact is reflecting the fact that the tip radius is on the order of 5 nanometers. If at the end of the day you repeat this experiment and you get a curve that looks like this last blue curve, then this last blue curve was generated with a tip radius of on the order of 15 nanometers. So you can clearly see by just monitoring the jump to contact point in a simple force distance curve, you've got some measure of whether the tip radius is remaining constant or not throughout an AFM experiment. So the first question just is a very simple question. It asks, what's the jump to contact when the tip radius is 5 nanometers? That value for jump to contact assumes that you use these input parameters, and it's basically just a check to see if you've done the simulation properly. You'll be able to read the value off from the chart, from the graph, and the jump to contact is about 1.2 nanometers, right? And I believe the choice listed of the 4 choices listed in the homework set, the correct choice is A. So this would just guarantee that if you get this answer correct, this would just guarantee that you've probably done the simulation properly. The next question involves a statement about the accuracy in measuring the jump to contact if the tip radius changes by something on the order of 1 nanometer. And that just simply means that you have to come in here and you have to measure, let's say, the jump to contact point for 2 tip radii that are different by 1 nanometer. So it doesn't matter very much what tip radii you select. You can vary the tip radius by plus or minus 1 nanometer. And what you'll find is that these curves are offset one from another by about 0.05 nanometers, right? If the change in the tip radius is on the order of 1 nanometer, right? So 0.05 nanometers, that's 50 picometers, right? So what the simulation is telling you is that if you're going to rely on this jump to contact and changes in the jump to contact position, you better have an AFM microscope that's got the capability of measuring the jump to contact position to an accuracy considerably better than 50 picometers, right? So this sort of sets a lower limit on the accuracy and stability of your microscope if you want to detect changes in the tip radii of 1 nanometer. So then you have to go and do some experiments and see if you can accurately measure changes in tip radii or changes in jump to contact with this precision in order to use this technique to monitor the tip radius during the course of an AFM experiment. So that's how I think about this problem, and gives you some indication of how VEDA can be used to answer realistic questions while you're performing research with an atomic force microscope.